Edexcel Decision 1, Graphs and Networks 4, the Travelling Salesperson Problem. Finding a lower bound. It's important to note that a lower bound won't be a Hamiltonian cycle. So what features should our lower bound have? Ideally, we'd like it to start and end at the same vertex, and we'd like it to visit every other node once. So in order to find a lower bound, we need to first choose a starting vertex. We then delete this vertex and all its edges. We then find a minimum connector, also known as a residual minimum spanning tree. And we do this for the remaining network using crisscross or prims. We then add back in the starting vertex with the two edges of least weight. Okay, so we're going to try and find a lower bound for this network. And we're first going to do it by deleting vertex A and all its edges. So I'm just going to scribble out its edges to remind us that we have deleted them from the network. Now for the remaining network, we need to find a residual minimum spanning tree. We're going to do this using crisscross. So the first thing we need to do is select the arc of minimum weight, and that is B to E, with a minimum weight of 7. The next arc of minimum weight is E to D, with 8. And then finally B to C, of weight 9. So the residual minimum spanning tree has a total weight of 24. We then want to take vertex A and we want to add it to our residual minimum spanning tree. And we do this using its two arcs of least value. So in this case it would be A to B and A to E, because they have values of 8 and 9 as opposed to 11 and 13. So A to B and A to E, which makes our total for the lower bound 41. Okay, so we're going to find the lower bound now by deleting vertex B and all its edges. So I'm going to delete its edges from the diagram to remind us of this. Okay, and again we're going to find the residual minimum spanning tree using crisscross. So the edge of least weight is currently 8, so that's E to D. The next is E to A of weight 9. And then the next one is A to C of weight 13. Since D to A would create a cycle, we can't use this edge. So that gives us a total of weight 30. Then we need to add B back in using its two edges of least weight. So that is B to A and B to E. And that gives us a total of 45 for the lower bound. Okay, so here's the algorithm for finding the lower bound, which we just did. And what we need to do again is we need to repeat this by deleting a different vertex. So in this network there were 5 vertices. We did it twice, and you'd still need to do it 3 more times unless told otherwise. And out of these 5 results we would choose the greatest of the lower bounds. Can you explain why? Don't forget, it's to do with minimizing the interval between the least upper bound and the greatest lower bound to hone in to the optimal solution. So if we repeat for all 5 nodes, we've already done A and B, we would need to also do it for C, D and E. We would get the results below. Now it's worth at this stage pausing the video and trying for yourself to get a lower bound for node C and for D and for E using the algorithm. So as we can see, we've got 3 unique answers for the lower bound. And we know that what we really want is the greatest lower bound. So the greatest lower bound for this problem is 45. So what's wrong with these solutions? If we look at the minimum connectors formed from performing the lower bound algorithm, we get something that looks like this when we delete A, and actually when we delete B, we get a similar looking graph. It's just that the nodes would be labelled differently. As you can see from these diagrams, we wouldn't be able to start and finish at the same vertex, visiting every vertex along the way. Therefore, this is not a valid solution for the travelling salesperson problem, but it is a lower boundary. So what do we know now about the optimal solution to the travelling salesperson for this network? So if we let the optimal tour be t, we know from the previous video that the upper bound was 48. And because the upper bound is a valid solution, we know that the optimal tour is less than or perhaps equal to 48. Now, so from this video, we know that the lower bound is 45, but we know that this is not a valid solution, so the optimal tour has to be bigger than 45. So we know that the optimal solution has to be greater than 45 or less than or equal to 48. So the next session we will be looking at practical problems.